Muscles Assignment 1.2 by Samuel Marsh. The muscle types. Cardiac muscle. This is found in the walls of the heart. It's involuntary, meaning that we cannot control it. They're responsible for pumping all the blood around the body in slow contractions. An example of this is the fact that we cannot control our heart rate. It contains cardiac pacemaker cells, which make up 1% of the total myocardium, such as the sinoatrial node. The other 99% is made up of cardiac contractile cells, which rely on aerobic metabolism. Cardiac muscles are important in aerobic sports such as marathon running, where oxygen is needed in the muscles to make them perform well. Anatomy of the cardiac muscles. The cardiac muscle contains myocardium, a muscular substance, which is made up of cardiac pacemaker cells, or the sinoatrial node, and cardiac contractile cells. Many nuclei are located centrally in the muscular cells, surrounded by mitochondria that anaerobically respire to provide energy. Branching fibres run throughout, with cells being connected by discs in it. The cardiac muscle cells overall have a thick and thin filament such as skeletal muscles. The cardiac muscle cells are responsible for pumping blood around the body, so muscles get enough oxygen to respire and carry on contracting. This is imperative in sports such as football, where midfield players must have the muscular endurance to run around the whole game, supporting the defence and the attack. Smooth muscles. The smooth muscles line the walls of the organs, such as the intestines. This enables them to contract, pushing fluids and solids along the digestive tracts and other hollow organs, i.e. the blood vessels. They're smaller than the skeletal muscles and are present in the eye, enabling normal vision to stay in focus. They are controlled by the autonomic nervous system, making them an involuntary muscle, so we cannot control them. In sports such as distance swimming, i.e. 1,500 metres, the smooth muscles must digest essential nutrients such as carbohydrates, which are slowly released and provide long-standing energy, so the swimmer has a sufficient supply of energy throughout the race so they can keep up with the competition. They produce long and slow contractions using the aerobic system for respiration. Anatomy of the smooth muscles. These are found in the walls of most of the gastric organs. It has a smooth microscopic pattern. They have a lac of myofibrils, which are tubes of muscle cells, sarcomeres, muscle tissues, and striations. It contains one thin layer of connective tissue named endomysium, meaning overall they're smaller than skeletal tissues. They only have one nucleus also, with narrow ends, causing them to adapt to new positions and eventually relax. Its function is to push fluids and solids along the digestive tract and hollow organs, as well as causing lots of other functions in other systems in the body. This is important in rugby, where lots of carbohydrates are needed to make the player have the correct amount of energy to last them the whole game. Skeletal muscles. The skeletal muscles are located in the appendicular skeleton, which go through constant contractions to enable movement. They're controlled by the central nervous system, making them voluntary, and without them movement would be incapable. These muscles are attached to bones by tendons. The skeletal muscles can either work anaerobically or aerobically, enabling them to go through respiration so the muscle can contract, either slow or fast. An example of skeletal muscles are the bicep, and are used in sports such as weightlifting when doing a bicep curl. They enable movement for the tendon located at the bicep, pulling the radius up to complete flexion at the elbow and complete the repetition. Anatomy of the skeletal muscles. A skeletal muscle is covered by a dense layer named epimysium, made of fibrous and elastic connective tissue. Underneath this lay some blood vessels and nerves, as well as many fasciculi, which are made up of myocytes, or muscle cells. The blood vessels contribute to the passing of blood, with the arteries bringing oxygenated blood, and the veins taking away deoxygenated blood. Perimysium, a sheath of connective tissue that groups together muscle fibers, running between each of the fasciculi. These fascicles contain bundles of cells, otherwise known as endomysium, inside of them, which contains capillaries and veins. When stimulated, skeletal muscles move to a specific part of the skeleton. For example, when the gastrocnemius is stimulated, the skeletal cells in there will move the tibia and fibula in the lower half of the leg. This is common in sports such as volleyball, where a performer must jump to return the ball back over the net and potentially score a point or return a serve. Functions of the muscles. Stability. One function of the muscles is stability, which allows the body to remain upright when necessary, but also allows the body to maintain a correct structure and posture in varying positions. The muscles involved are voluntary muscles, such as the abdominal muscles, and are controlled by the central nervous system. The muscles involved are attached to tendons so they can contract and move specific bones so the body can move and be stable. In football, when completing a throw-in, the abdominal muscles contract and hold the body on the sagittal axis so the arms can effectively move forward without the body bending in half and ruining the throw. Heat production. Heat production is crucial. Its function is to warm up the body but also the bloodstream, so the blood flows better to enable a better supply of oxygen to the muscles. The skeletal muscles involved are controlled by the central nervous system due to them being voluntary. They are attached to the bones by tendons, being able to work anaerobically or aerobically, contracting slow or fast. These muscle contractions produce heat, causing up to 70% of the body's total heat production from the muscle tissue. Heat production is important in sports such as football. The heat given from warm-ups decreases the blood viscosity, allowing blood to flow well and allow more oxygen to be supplied to the muscles more efficiently. Motion. The skeletal muscles are controlled by the central nervous system, which controls the motion of the body. Motion is a voluntary movement. It primarily occurs in the appendicular skeleton, where the limbs of the body are located so movement can occur. The muscles contract and cause movements at the joints by different tendons pulling on different bones to create fluid movement. An example of this is when a sprinter runs their 100-meter race, where the muscles in the quadriceps and hamstring group contract, causing the hinge joint in the knee to move the leg back and forwards to generate a running movement. Circulation. For circulation, the muscle type involved is the cardiac muscle and the skeletal muscle pump, both of which are involuntary and happen all the time. The cardiac muscle is responsible for pumping the blood throughout the body, supplying the muscles with oxygen found in the oxyhemoglobin so they can respire and enable contractions. Myocardium is found in the walls of the heart. The skeletal muscle pump is a collection of skeletal muscles that aid the heart in the circulation of blood. In every aerobic sport, such as marathon running, circulation is required as it enables the oxyhemoglobin to be travelled around the body so it can be supplied to the muscles. Digestion. Digestion is carried out by the smooth, involuntary muscles that are controlled by the brain. These muscles are smaller than the skeletal muscles that use anaerobic respiration. Digestion allows us to take in nutrients and energy from our food, which is crucial in sports such as marathon running, where athletes require lots of slow-releasing energy from carbohydrates to compete with the rest of the competition, so the muscles do not become tired fast, but instead will last the entirety of the race. Here are diagrams of all the muscles. Origin and insertion. Skeletal muscles are attached to bones throughout the body via tendons. The origin is where the attachment of muscles is fixed and does not move during contraction, whereas the insertion is the attachment site that does move when muscles contract. When doing bicep curls, the point of origin is the scapula and the insertion is the radius. Flexion and extension occur at the synovial hinge joint, as when the bicep flexes, the tendon connecting the radius pulls the arm up and on the frontal plane and sagittal axis. Here are 12 examples of origin and insertion in the body. The different muscle fibers. Type 1, otherwise known as slow twitch muscle fibers. These contract slowly, but can contract multiple times, suited to aerobic activity due to the aerobic energy system they use in having a high resistance to fatigue, with a low force in the muscle itself. They are required to contract multiple times to complete multiple repetitions. This relies on the blood supply in the muscles so they can respire. All the oxygen they receive causes them to be red muscle fibers. They have very slow aerobic metabolism, meaning food is broken down slowly and enabling them to work for a long time. Sports such as marathon running or 1,500 meter front course swim use this muscle type, as contractions are needed to produce multiple repetitions of the movement. Type 2A, also known as fast twitch oxidative fibers. These have a fast contraction speed and both use anaerobic and aerobic energy sources, metabolizing with both. They appear to be white fibers due to having a lower necessity of oxygen compared to type 1. This means they have a lower resistance to fatigue and will fatigue fairly quickly. Type 2A have a fair amount of mitochondria and also a fairly wide capillaries. They are suited to a 400-metre runner and 11-a-side football game, as they can work both anaerobically and aerobically, which are both crucial for football, sprinting the whole game, and having the muscular endurance to last the whole game. Type 2B. Type 2B are fast-twitching glycolytic fibres. They are white in colour, similar to Type 2A fibres, due to the low level of myoglobin they receive, and also having few mitochondria. Due to this, they fatigue the quickest out of the three types. They are dependent and have very quick metabolism, breaking down food fast. They can be turned into Type 2A by resistance training. The amount of force they exert is high, but can only be used in short bursts of contraction, but not long distance or time, as they do not have enough mitochondria or myoglobin to respire enough. They are suited to sports such as the 100-metre sprint and the 110-metre hurdles in athletics, due to being able to work for short periods, giving maximal power from the contractions, and also using all the nutrients given from food. And here is an example of the muscle fibres worksheet. How fibres are used in sporting events. In football, all of the muscle fibres are used at various stages. Type 1 muscle fibres are used throughout, providing excellent muscular endurance, enabling the performer to reduce fatigue felt and continue to perform at a high level. They have a slow metabolism, which means they continually digest food, giving them efficient nutrients throughout the game so their muscles can contract when losing speed over longer periods. It also means their kicks will not get weaker due to fatigue, and they can continue to pass and shoot with the power and precision intended. Type 2A oxidative muscle fibres are useful in football, as they enable the performer to put pressure on people with the ball. They are able to run at the defender, meaning they have to move the ball and potentially make a mistake. They can be used to stay in position, jockeying the player that they're marking. They can metabolize anaerobically and aerobically, meaning constant speed and endurance can be applied without losing one of them to the other, being fairly resistant to fatigue. Type 2B fast glycolytic fibres are imperative in football as it enables them to sprint, being the deciding factor in getting a goal or getting past the defender. They enable explosive anaerobic movements due to their increased power and shortest contraction time, meaning they can complete more contractions, increasing limb movement. If they did not have any Type 2B muscle fibres, then the attacker would not be able to beat the defender and would get tackled and not score a goal and contribute to the team. How the experiment showed the use of slow, and fast muscle fibres. During the cycling experiment, all three muscle fibres were used. For example, Type 1 slow contracting fibre were used throughout, enabling the participants to carry on cycling, despite the added resistance due to the constant and slow metabolism they were providing, not fatiguing. They're not as powerful as fast-twitch muscle fibres, suggesting the initial power output being lower. Person 1 has more genetically produced Type 1 muscle fibres, due to the fact that their recording started at 73 and their power output finished at 63, showing a shallow drop overall, but nothing compared to person 2. Their recording started at 112, before sharply rising to 155, before dramatically dropping throughout, showing a high percentage of Type 2B fibres. Fog muscle fibres showed a maintenance of in the intensity of the workers as they're recruited, due to being able to work aerobically and anaerobically, but it does vary per person. Person 1 has more fog muscle fibres than person 2, due to the fluctuating but semi-constant power output through the exercise. Fast-twitch muscle fibres showed an extreme amount of force being exerted than the other two muscle fibres, showing more power, but also a much steeper drop in power after 10 seconds due to them working anaerobically and being able to keep it up. Person 2 has a much higher percentage of fast-twitch muscle fibres due to their power recordings, because they started at 112 and then rising to 155. From there, the muscles became fatigued, showing as the recording dropped from 60 and varied from there on.